So we need to wait maybe about 10 seconds so it actually goes live. And I will present to you. Thank you for
Yes.
accepting anyways.
Mhm. If there will be people coming from, let's say, criminal department or criminologists.
Well, I sent to all of them in the university here, so I hope that some of them
Mhm.
will attend. I'm hoping so. I advertised to the criminology department in the
Perfect.
university here. Okay, so thank you, everybody, to being here. This is another statistics department seminar. Our guest today is Jorge Mateu. He has this very vast CV. I'm pretty sure that most of you know him. He has more than 300 publications, 16 books, 29 PhDs, has a fellow of the Royal Society and many others. If you go to his website, he likes to put some very interesting phrases there, motivational and others. So he's very active in our community. And it's my great pleasure that you accept my invitation. I'm really excited to have you here. I had a chance, I don't know if you remember, to meet you at Spain once when I visited Luis. I went to Jaume just to get to know the department and visit you. At that time, I was thinking in a postdoc that ended up not never happening. But anyways, so it's a great pleasure to have you. So we're very excited to your talk, and the title is very interesting. As you mentioned, I also invited the people from sociology and criminology department from my institution. So hopefully they are at the audience at YouTube. Okay. So you have 50 minutes to do your talk, something around that, of course. And then we go back to the questions from the public. And thank you for accepting my invitation.
Thank you very much, Marcos, and thanks all the audience that it's right now online listening to me. It's a great pleasure. And now that Marcos has mentioned his visit to me, I perfectly remember. Although this is something like maybe 15 years ago or something like that, but it would have been nice to have you here as a postdoc. In any case, here we are. This time is online, but probably I really would like to visit you, Marcos, and all the people around you there in your department sometime in the close future.
That'll
Let's
be
say it like
great.
that, right?
Yes.
That would be great. In any case, let me just share my window with the presentation. And as Marcos said, in the title, everything is there. I mean, the thing is, you see that. Well, I have lots of slides, so I really don't know how much. I have around 15 minutes, but I don't know how much I will speed up to go to the very end. But in any case, the idea of this seminar is to give an overview on, let's say, on problems having to do with infectious diseases and crime data, where the problems they are very much based on space and space-time point processes. It's not. I mean, people working in spatial statistics, they are very much used to work on geostatistical problems, on count data, on aerial data, but they are not much on working with directly locations, geographical locations of the events, which is point processes. And this is the aim of this seminar, to provide this overview on particular methods to deal with events having to do with spatial temporal point patterns. So let me just, as you see in the title, I will be talking about epidemiological problems, infectious diseases first, and then I will come down to crime data. I will try to speed up to go to the two, let's say, two parts here within the seminar. So this is just some of the topics I will be talking about in the first part, in the epidemiological thing. Basically, the three of them, points 2, 3, and 4, are based on recent papers since COVID came. Since COVID came, you know that many people are working on public health problems having to do or very much related to COVID data, and the same I did, and this is the result of these 2-3 years of COVID with us. So the very first thing, well, this is in terms of epidemiological thing, and then the topics I really would like to talk a little bit about crime data analysis. Well, they have this kind of let's say of main topics. I will be talking about detecting focuses and generators of criminality in cities. So there are particular areas, particular landmarks in the cities that they can be generators or inhibitors of criminal activities. So I will be talking how to detect these sort of things. Then I will go a little bit more on the probabilistic aspects of criminal patterns. I will introduce a little bit more on, now that it's kind of peak and everyone works on machine learning and deep learning methods. So I will be talking a little bit about how these machine learning methods can help in our prediction and classification of crime data in cities. Then what happens when we have lots of data and then we have to reduce dimension of this data? Then it's kind of how to reduce dimensionality of the data, having to do with body centers and and just a kind of a specific and mathematical thing having to do with differential equations, again included in spatio-temporal point processes. Let me just then start with ideas on motivating ideas on COVID data. So as you see, I'm sure that most of you that are right now listening online, the seminar, have been working with, well, in general with diseases, with infectious diseases, but in particular with COVID data. And most of COVID data, it comes in terms of aggregated data. In subregions, we have a big, let's say, city or a big country. We have subregions on them, and then on the country, and we just count, we aggregate data on them. This is the classical approach, and this is something that we are very much used, for example, to have maps like this one, where we have the big region, we have subregions on them, on the big regions, and in particular, we have this counting, aggregated counting data. This is the classical thing, but we don't want to go into the classical thing. We prefer to go into this more accurate information in terms of geography, in terms of geographical coordinates. And what we observe is locations of X, Y, and T of COVID data, of infected people of COVID data, right? So the thing is that now we go into the very much more disaggregated type of data where we have a space-time point pattern. This is difficult to get. Yes, I know. This is really difficult. I was lucky during these years to get this type of data. This comes from Cali in Colombia. And I will show you also some data, some COVID data from Valencia in Spain. But yeah, I know that this is really, in terms of confidentiality and all these sort of things, it's kind of a problematic thing to get this type of data. But if we are able to handle, and we are able to have this available data for us, then it's perfect. Then you will see that we can go deeper and deeper into the spread of the disease into a particular city, for example. So this is the type of data that we are analyzing here. For example, this is in Cali in different moments in 2020, March, May, July, August, and you see how the spread was going on from very few very few locations, so infected people during March. Then it went increasing in May and very much spread out through the whole city in July and August. So the spread is what we will be analyzing here. Now, well, this is the papers that we've been working with during these 2-3 years of time. And and let's go to the very first approach. The very first is what we call a mechanistic space-time spatio-temporal modeling framework. So the motivating example here is Valencia City in Spain. This is just a part of Valencia City. In particular, it only has 4 districts, and you see here the building locations in the study area in these 4 districts. It assumes a number of population of around 350,000 population. The total in Valencia is around 1 million, 1.2 million inhabitants, but in particular, we're only working with these 4 districts in Valencia. And there, what we have is basically locations of infected people within these 4 districts. Well, within these 4 districts, we also have the census tract, over which we will have information I'm going to talk about right now. And we have 111 census tracts in the study area. Well, this is the COVID data. So you see how it evolves again in April 2020, where we have a number of infected people around this for subset of the city. Then in August we have much more data, and basically in November 2020, basically the four districts were covered by COVID cases. So clearly the spread throughout this region is clear through time. So now we have some additional and very interesting information here, which is human mobility data. We were able to have how many people, this is aggregated data, how many people were from one, what we call moving area to another moving area. So this has to be included in the model, and this is kind of new thing. It's kind of very important thing in terms of infectious diseases, and clearly has to be included within the data set, and finally in the modeling framework. And this is what we did. We were able to calculate the probability of movement from one area A to another area J or over a particular week, and we just calculated a ratio between the mobility flow from these two areas divided by which is the size of the population in, let's say, in the origin area, in area A. With this, we have these probabilities and have things like this. These four districts were divided into seven mobility areas, and you see in these different graphs the metrics, for example, of each particular week. In particular, here I selected week 11 and week 15 of movement from each one of the seven moving areas into themselves, into these seven moving areas, right? So, and this in terms of probability. So this probability, how many people in terms of what is the probability of going from one area to another area, you will see that that will be included into our model. But we have additional data in our census tracts levels. For example, we have socio-demographic data. We had something like the percentage of elderly population, so people aged 65 onwards. We also had percentage of young people from 18 years old or lower than 18 years old. And then we have some economical indicators like average income per person, and finally, of course, the population density living in the area. So this is at the census tract level. And yeah, and with all this sort of information, so our approach has to do with point pattern, with space-time point pattern modeling. And here we have two important things. One thing is the first order spatiotemporal intensity. As you see here, it represents the rate at which events occur in space and time. So basically is the expected number of events that will be observed around a particular event. And we have, this is the, let's say, the overall first order intensity, but we also have, when we condition on the past, on the history of the process, so we have the corresponding conditional intensity, which clearly characterizes the whole space-time structure of the point pattern. And this is our aim, modeling, providing a model for this conditional intensity in a way which is called mechanistic models, which basically what we provide is a realistic way of modeling the intensity function based on sound science around this thing. This is there is another option, I mean alternative option to mechanistic models, which is the empirical models, but we're not going into them because we believe that mechanistic models here, they provide much more insight and deeper insight into the problem in question. Right, so within this framework, space-time conditional intensity function. So our model basically is divided or is split into three terms. A term which depends only in time, this is mu. A term which depends on only space, this is lambda. And finally, a stochastic term which depends on space and time. It's kind of residual space-time structure there, right? The first two terms, mu and lambda, are basically deterministic terms. They are based on covariant information, one on time, the other one on space, and everything which is not deterministic goes directly into the residual term, which is a stochastic spatiotemporal term here. Because they are kind of deterministic, there are different ways. In fact, I should say there are many ways to model this mu and lambda. Here we selected one very simple way for mu, which is a kernel density estimation for mu. This is non-parametric because at that moment we didn't have time, we didn't have covariates evolving in time. So a simple approach was this kind of KDE for mu, for the temporal trend. For the spatial intent, we had all these sort of spatial covariates. So what we did is we consider our 111 census tracts. We consider the counts, how many infected people lived in a space or in each one of these census tracts, and we consider a negative binomial distribution, negative binomial random variable over these counts. The reason of going through negative binomial rather than Poisson is because we observe over dispersion, and clearly the over dispersion has to be tackled much more using a negative binomial rather than a classical Poisson distribution. Fine. So with our negative binomial, we had two parameters. Phi parameter clearly goes through the parameter that controls for this over dispersion. And the first term, we have this capital E, which is a kind of offset, which will be kind of population density, how many people are living in the area. And finally, the important thing here is this small ri, which is the relative risk at that particular census tract. And there is where we impose our model. In particular, we impose like two terms in equation 3. The first term is based on let's say spatial covariates. The spatial covariates I mentioned before, this is linear, simple thing. But because we didn't have enough with that, we helped the model in, let's say, in disentangle the stochastic elements that we could not control. And there we added these other two terms, U and V. U and V, you see, they depend clearly on the census tract. U and V are, let's say, random spatial effects. The U are kind of structure terms. In those of you that are familiar with aerial data, you know the BYM model. So basically, we follow the BYM model for the structure terms, which in a sense, it provides information on the neighborhood of a particular census tract, and this neighborhood provides, let's say, comes into the mean and into the variance of a Gaussian random variable attached to the UI. Well, and the VI are unstructured random effects, which basically they are Gaussian distribution with mean zero and a particular variance of that effect. So the whole thing provides information on the counts, and then the counts are basically integrated, dividing the count by the area of the census tract. We provide our output thing is basically our lambda, which is the intensity function in a space that we are looking for. Fine, but then it comes the space-time term, which is kind of hidden. It's not observable, and we need to know a little bit about that. How to do that? So there are several possibilities. Our main possibility here was something like that's fine. So our stochastic term in space and time could be just the product of functions, which is these g functions depending on past events. So y depends on x, which is my current event, and xj, which is all the set of previous events happened before t. Fine. And this g function, which is in many cases in public health problems, it's called like the transmission kernel function. Well, it's a parametric function that you see here in 5 that depends basically on two parameters, theta and phi. Phi, as you see, it's basically it's the ratio of the distance over phi. So phi, in a sense, it's a kind of scale parameter controlling distances, and theta provides the effect, the strength of the interaction with respect to the past. If positive theta provides information on that there is an attraction, so there is a kind of clustering degree. A theta which could be negative, that's an indication of inhibitive behavior with respect to the past. And finally, theta 0 would mean that f equals 1, and basically there is nothing there. There is no interaction with respect to the past. But this transmission kernel, you see, depends very much on the distance, the physical distance, but there is nothing here in terms of the human mobility that I've been talking about. So there is a way to modify this transmission kernel by considering the human mobility. And then we come to this expression here for G. Well, you see that when, so this is the transmission between X and XJ. So if both of them, the location at X, the event at X, and the event at XJ, they belong to the same moving area, fine. We only consider our f function, which is our previous transmission kernel function in 5. But what happens if they are in different areas or in different parts of the city? So clearly, if they are different part of the city, we have to consider the human mobility between these parts. And then it comes this kind of complex combination that you see that depends very much on pi, and pi is the estimate of the probability that a particular case, J, visited the corresponding mobility area where X is located. So with this kind of, let's say, convex combination that takes into account probability of movement, takes into account f over distances, physical distances, then we provide much more insight on not only how close I am to an infected case, but also what is the effect of people moving from one area to the area to another area. That's fine. So we come into because there are a set of parameters involved here, and we come into the likelihood function for these types of models. But the problem with the likelihood, which is the first expression we have here, is that we have a double integral, which is in space and time, which is quite complicated to develop or to calculate. And then we prefer to go into a little bit more, let's say, easy task, which is the partial likelihood. You see the partial likelihood, we have this sum over the logarithm of ratios, and then basically in the denominator of 6 we will have one integral, so there is no time here considered. So we have got rid of one integral over the 2 that we have in the full likelihood. This is one thing, but additionally to this, from 6 to 7, the integral of w in a sense is like saying, tell me where the new locations will be. But the new locations for us are addresses where the people are living in the buildings. And we had, well, didn't mention, but we had something like 6,513 buildings in that area of the city. So basically, that integral in 6 in the denominator transformed into just a sum over this number of buildings. So equation 7 is a parametric equation on theta and phi, and it's quite easy to be developed in terms of computational things. Fine. And then in terms of practical, in terms of the results, well, this is mu, this is the overall trend, and you see clearly over from April 2020 to January 2021, you see clearly how let's say the temporal trend, which means the evolution of the spread in terms of counting in time has been developed during this time. We can see in January, which we had like the second or the third peak of or wave, and it's been clearly noted with this mu. Well, this is one thing. The overall spatial intensity in our region, calculated in terms of, remember this equation where it has on one side a simple linear model on the spatial covariates, but we added random effects, the U and V. This is the overall spatial intensity, but we can do something like this. On the left hand side, we have the spatial effect estimate. This is U plus V, so the random spatial effects are included here, and on the right hand side we have the probability. We can calculate things like what is the probability that the relative risk is above 1. So clearly we can go deeper into, let's say, into the modeling strategy in terms of detecting where there is more, let's say, where the probability is larger in terms of getting infected. Fine. Well, these are the parameters theta and phi. You see that there is a kind of additional we call nuisance parameter, which is C7, which is 1 week or 2 weeks or even 3 weeks on the history, because rather than going completely from the very starting point in the history, because this was COVID and it was known that when one is infected, it's because it was really. One is that when the infection is detected, it was something like several days before that when that person was really infected, right? So these several days, we considered that there was no need to go, weeks and weeks and weeks before that in terms of history. So just to let's say to keep computational a little bit downwards, we decided to consider these three: 1 week, 2 weeks, and 3 weeks for the history. In any case, you see here that when c equals 14, for these values of theta and phi, we get, let's say, the best option or the best estimated parameters for our data in terms of the log likelihood or log partial likelihood. And this comes into this thing. This is the stochastic term. It provides information that the infection rate, it goes down quickly in terms of distance, in terms of meters, to down to, when we are more than 10 meters. You can see here that basically the infection disappears. So in a sense, it provides a clear analytical way to obtain information on how the procedure of being infected behaves in practice, because we have a clear exponential, a decaying exponential in terms of distance, that has a particular analytical form. Remember that this is a kind of analytical form for the stochastic term that has to be added up to the lambda, which is the spatial intensity, and to mu, which is the overall trend. And all of them provide information on in our conditional intensity function. Well, this is one thing, but we were not that happy with that. Why? Because clearly the spread was not homogeneous, and in general, the spread of COVID, or in general some kind of these infectious diseases, they are clearly non-isotropic within an area. So we decided to go a little bit farther in this line, and we're using another type of data. In this case, in Cali, in Colombia. Cali is a larger city than Valencia, compared to Valencia. In particular, it has around 2.2 million inhabitants. It's the second largest city in Colombia. And here we also had information on X, Y, and T, so the locations and times where one particular person was detected infected by COVID. In total, we had something, as you can see here, of 38,000 individuals over 28 weeks. Basically, it went from March to September of the same year, 2020, and you see clearly the spread of the events. So from very few cases March to really, I mean, basically the whole city of Cali was covered by infected people in July and August of the same year. Fine, we consider, well, we had additional information. One is the population distribution in the city, but something which we did not consider in Valencia, which is what we call marks. For example, particular locations of schools, of churches, of town halls, that you will see they play a very important role in modeling, in our modeling strategy right now. So one thing is consider, let's say, kind of homogeneous behavior all over the city, all over the region of a study. Another thing is say no, because I'm close to a church, I'm close to a school, the spread there was much higher, or much important than in another parts of the city. So these landmarks, they will play a very important role here. Fine. So we go. The general setting is the same in spatio-temporal point process, but now we change our strategy. Basically, we go to something which is called self-exciting point processes. The overall idea is the same. We aim to model, to provide a model for the space-time intensity function, right? This is equation 8. But now the difference is that, well, there is a background intensity. This is lambda 0, fine. But then we have something which depends on a k function that it depends on space and time, and this k function is called a triggering function, a triggering kernel function. This provides, let's say, the strength or influence of past events into current events. How to model this k function? That's the important point here. If we go to classical, let's say, to classical approaches, this k function is modeled under stationary, let's say, regimes, right? So assumption of stationarity is something very well known, and it's a simple thing. Using, as you see in this equation here, a diffusion kernel, right? But this has a problem, and the problem is that the spread clearly is not behaving in this kind of general Gaussian diffusion, but it's spreading in very different ways. So stationarity was not an option here. So a way to go into non-stationary, let's say, k function, triggering functions, it's by we decided to say, fine, our k function is split into a function which depends on in time and a function which depends on in space. The one that depends on time, you see, this is in new TT prime, is basically a classical Gaussian kernel function, stationary in time. This is no problem. But then we went into the spatial part of this triggering function. How to make things non-stationary? We were helped by a result in Higdom in 1988, where basically the way to define a non-stationary Gaussian process is by considering allocation of zero mean normal random variables. This is the xi, and then we define the corresponding kernels over a number of knots. So we define over our region a knots, and then kernels over the knots multiplied by these zero mean normal random variables. With this, we have a Gaussian process. But this classical result it's not a problem, but in any case, it's an approximation. First, what should be the number of R? This is discrete, and so this is just, let's say, a finite sum of let's say, of weighted zero mean normal variables, right? But how finite should it be? So we decided to say fine, because we don't want to be finite. We want to be continuous rather than discrete. We used neural networks to consider a continuous representation of this Gaussian process over the whole, let's say, region of study. And that was our approach. So our approach, I don't want to go deeper into this detail because this is a little bit more formal or mathematical, let's call it that. But in any case, we decided to have as our let's say, V of SS prime, the inner product between two feature mappings. The inner product being understood as the integral of the product of two functions, fine. And these two feature mappings are, as you can see, phi s is basically a weighted, let's say, weighted sum of some kernel-induced feature functions, ks. So basically, we have a number from 1 to r, so we decide which is r, and then we have weights that multiply to some kernel functions. So if we plug this into the above expression for v of ss prime, so we end up with the expression that it is basically in the bottom of this slide, and this is basically what we have to compute. But now we have an additional result here, because if we go again to the classical thing for these kernel functions, we can use classical, let's say, Gaussian functions. And again, these Gaussian functions, they should be kind of isotropic things. To make them anisotropic, then we need to go to this thing which is highlighted in red, that there exists a one-to-one mapping between a bivariate normal distribution and its one standard deviation ellipse. So we went from the normal to ellipses of one standard deviation. The way we did that was using this pair of focus points, and then with the focus points we transform sigma sub s, which is the variance covariance matrix of the normal distribution, into another sigma s, which you can see here at the bottom, which is clearly anisotropic and based on ellipses rather than, let's say, circles. This was the way that we were able to let's say, to put anisotropy into our context and into our modeling framework. Finally, if we want to consider landmarks, remember these particular locations within the city, fine, we just have to modify our likelihood function and then consider this term in the center, which goes from L1 to capital L, which is the number of landmarks, and these are just the weights, gamma L times G, where gamma L is the weight associated to a particular landmark. So here we have two important things. What is the weights? We have to estimate these weights. That will be how much important, what is the importance of a particular landmark. And this G, which is basically a Gaussian function, which is defined in terms of sigma, or the variance covariance metrics. So again, we have to estimate the sigma sub L, which provides information on the variability and on the uncertainty in the estimation of this function associated to landmarks. Fine. So, well, in our when we went to fit this type of model to data, we compared to classical things. For example, a random model where nothing is happening. We compared to SIR, which is this compartmental models, very well known in epidemiological studies. We just consider also an autoregressive of order 3, ITES model, which is a very also classical model in let's say in space-time earthquake modeling. And finally, this is our approach, NSSTPP, which is a non-stationary space-time point pattern without any, let's say, landmarks. And finally, the very last row, which is our full model, which is our approach together with landmarks and R equals 3, remember, is 3 types of feature mappings that we consider in our strategy. So let's just skip this one, but I would like really to mention this one, this is something I really like, which is you see here two things. One thing is let's say arrows or segments of varying longitudes, right, in red, and varying, let's say, orientations. This is indicating this is they go for each location. We calculate the focus points and the length between two focus points, and we represent this by these let's say red arrows. And here we can see not only, I mean, the influence of the spread in terms of directions, in terms of orientations in the city, but also the length. It's indicating how strong is the effect in particular locations. So this is very clear. This is very motivating in terms of our modeling approach. And the colors beneath the red things, which you see it's blue or blue in parts, they are the weights associated to these feature mappings. So sometimes they are homogeneous over the region, but sometimes they are stronger in parts of the city or in other parts of the city. Well, and with this, we're able to obtain the spatial influence, which again, our non-stationary model provides very clear information on, depending on the spread of the infection of the infectious disease of COVID data, depending on where we are. It's not the same if we are in the northeast or in southwest or in other parts of the city. So clearly, the spatial component is absolutely important in our modeling strategy. These are the landmarks. So on the left hand side, the uncertainty estimated for each landmark. On the right hand side, the strength of each particular landmark. So we can clearly see, depending on where we are, depending if we are in churches, if we are close to schools, if we are on the town hall or whatever, we can see that we can measure how important is the infection in those particular places. Yeah, and finally, this is our conditional predicted condition intensity function all over the city of Cali. Fine, because let me see what is the time. Fine. So the third and final thing I really would like to mention, but because I want to go also to crime data analysis, this is very important. This is ongoing work because it's called velocities, because that was again a side effect of the previous things. Because one thing is saying fine, the spread is going in this direction with this type of orientation, and we saw, just by looking at these sort of things, like here, we clearly saw that direction is important, that anisotropy is important, and the spatial influence is absolutely important and should be there in the model. But there was something extra, which is on what is the velocity of the let's say of the spread. It's not the same that everything is smooth, that the velocity of the spread, so the rate of infection moving around is low, that is high. So we were able to consider something which, let me just go quickly into this thing, just to give a very overview of the subject. The thing is that this lambda that I've been talking about before, now we consider that this lambda is driven by an SPDE, stochastic partial differential equation, which depends on a spatial growth function. By doing this, so plugging into lambda, this sort of, let's say, mathematical development based on SPDEs, we are able to provide something which we believe it's new at the moment, right? So what type of function? We consider several types of initially of ordinary differential equations. We started from simple things like linear, or waveable, or logistic, as you can have here, but this is known. But then we transformed this ordinary differential equation into partial, because we were talking about time, space in direction x and direction y, and finally it's stochastic, because we provided a spatial growth function into this stochastic equation. So, well, finally, with some development, we were able to obtain velocities, and with these velocities, this is some development. Again, if you are interested in this, just let me know by email, and I can send you proper information on this. But with this particular, for example, this is an example of a Weibull model inserted. So, where lambda is basically given by this expression here, and the important thing here is you see, for example, in equation 16, there is in the power of t over t sub 0, there is an r of s. This r of s is our spatial growth function, and there is where we put our stochastic model. You see there, the spatial rate r of s is given by mu of r plus a Gaussian process here. And there is where we put inside our stochasticity and make everything SPDE. Well, with this and calculating several things, we are able to obtain things like, for example, well, this is our estimated intensity, but this is the partial derivative of intensity over time in the region of Cali. Again, the data set we use here is the same as the one I've used in the previous, let's say, section. This is the partial derivative of lambda with respect to the direction x, with respect to direction y, and very important, the very final thing, which is, we are able to obtain two things. First, the arrows. So dividing the region of interest, in this case the city of Cali, in small, let's say, quadrats, in small grids, we're able to obtain directions of maximum velocity. You see? So it's not only direction. So tell me where I am in the city, and I will tell you the spread in the maximum, let's say, velocity of the spread in which direction is taken. But also you have underneath some colors. The colors again is the let's say the norm of the velocity, right? So we have the magnitude of velocity and the direction in which this velocity has maximum or minimum, depending on our interest. So this was kind of new thing. I mean, it's not only tell me where this, how is this spread, but also tell me how, when the infections are moving around quicker or smoother, depending on where we are. See, this is called so velocities. Again, in particular cells, tell me where I am. For example, here in cell 911, fine. The main direction here of the spread is 200, around 290, 93, 94, and this is detected by our model. So directions are something important here. Now let's go in the next, let's say, 10 minutes. Let's go to talk a little bit about crime data, because I'm really interested in this, in the sense that um, I'm sure that this is an overall, let's say, thing that police, they don't want to be, let's say, reacting. They want to be, this very last sentence I have here, which is they want to be smart, they want to be effective, and they want to be proactive. So proactive policing rather than reacting policing, right? So the only way to be proactive is knowing in advance with particular probability what will be happening. This is the only way, and this is the way we try to help, let's say, police in these actions, right? Well, this is a very simple thing, but it's very clear, or highlights the whole thing. So data collection, from data collection, we have all sort of data. We put everything there, this data fusion, and we analyze our data. With our analysis, we provide predictions. But of course, the predictions, they go directly into police operations, because police, in a sense, they trust our predictions, so they react to them. And because there are some police actions, of course, that provokes, that provides some kind of, let's say, criminal response to these operations. And again, this criminal response goes into data collection, and we have the whole thing together. And where we are in terms of statisticians, we are in the part, of course, of data collection and analysis of this data in terms of our modeling strategies. Fine. Well, now, the very first approach. Just assume that we have a city, and in particular, the data I'm showing you is for the city of Valencia, again in Spain. And we have a city, and we have counts of a particular, let's say, crime happening in the city, right? And a very simple approach. This kind of, yeah, I divide the city into small cells. I count how many data I have there. This is only space, no time at the moment. I count there, and my counting variable, because this over dispersion, is negative binomial. This is kind of close, similar. It has some similarity to one of the models I've shown you before, right? Negative binomial. Now we have two parameters: the over dispersion parameter and the mu I. Over mu I, we have, let's say, our modeling framework has several things. One thing, well, is this log of EI, capital EI, which is the population, is an offset. What is the population living in a particular cell? Fine. Then we have some covariate information. This is our capital X, and we have the second term, totally deterministic in linear form. Then we have something very interesting, which is could be kind of similar to transmission kernel. Now we don't talk about transmission kernel, but this has to do with distances to particular focuses. Remember that we are interested in saying if I'm close to a metro stop, that will, let's say, attract more, or will rise the number of, let's say, criminal acts when I'm close to there, or will inhibit the number of criminal acts close to a metro station, for example, right? So we have some focuses. These are, let's say, the J from 1 to P, and we are able, using this formula of F, to obtain a function that depends on the distances to these focuses. And again, this depends on two parameters, alpha and beta. If alpha is larger than 1, it represents an increase or a decrease in crime risk at those particular places. So with this simple model, we're able to obtain, but I think this for you won't be that, well, in any case, this is the representation of F. You see it's 1 plus something. So the representation of this function when it is fitted to data, and we have alpha and beta, then these functions could go from, let's say, upstairs and with a decrease down to 1, or could be just starting from any place between 0 and 1 and increase up to 1. So if it decreases, so on top of 1, it decreases down to 1, it's an indication of, for those distances, of an increase of activity, of criminal activity close to a particular place. The colors indicate these places. For example, we have bus stops, we have department stores, we have police stations, schools, etc. So we're able, place by place, landmark by landmark, to provide information on an increase in the criminal activity or a decrease in the criminal activity. And then we can go to the police and obtain things and show them things like this. In Valencia City, on the y-axis, we have bus stops, department stores, police stations, schools, subway entrance, supermarkets, train stops, university, or whatever. We analyze here three types of, let's say, crimes. One is property crime, robberies, and vandalism. And we just consider something kind of very simple information for the police, plus or minus, saying no. For example, if you are working on a, let's say, on, for example, in terms of robberies, which is the, let's say, the second entrance here, in terms of robberies, you see that robberies, clearly we have a plus in red close to department stores, which is kind of expected, but here our model clearly outlines this sort of behavior. And we can obtain things like this, for example, in the city of Valencia, with these small grids, and in colors we see what we call high risk maps of criminal activity, and the colors indicate the blue one is for properties, for property crime, the red one is for robberies, or vandalism is the yellow one, and then we can obtain, let's say, this high risk map individually for each one of the three. We can say, no, tell me where we have high risk maps when both of them, property and robberies, are happening together, or when the other two, or even, for example, in this case, in the black thing, when the three of them are being, let's say, high risk, so happening at the same time in the same place. So we can handle this sort of information, which is easy to explain to the police. If we're going to go a little bit more, let's say, probabilistic, then clearly we need to go deeper into some modelist strategies. And for example, we here I just want to mention let's say, analysis of crime data in Bogota, in Colombia, where we have homicides, simple thing on homicides, but we also have some kind of car thefts or motorcycle thefts. This is just kind of, let's say, over some years from 2012 to 2018, the time series. But also we have commercial thefts, so thefts to department stores and these sort of things. Or finally, thefts to people moving in the walking in the city, and then you're stealing whatever, your pocket, whatever, their cell phone, and then so this is what we call person thefts, right? Fine, but this is in terms of time series. Clearly, we have the same sort of thing in terms of space. This is the region of interest within Bogota, and this is the locations of homicides in the city. You see that there is a part of the city, let's say in the west part of the city, where we have much more concentration of homicides happening here in the region. But the same kind of thing in terms of space. So car thefts on the left hand side, or motorcycles on the right hand side, commercial or department stores thefts. And you see on the right hand side that so thefts to person, no, to people. So you see that you see this kind of map, you see, no, I'm not visiting this area because basically, independently of where I am, I will be stolen in a sense, right? But clearly this is space. Time is not considered in this map. In any case, well, and additionally we have, let's say, covered information. For example, distances to water places, distances to pharmacies, distances to transport means, distances to parks, and all these sort of types of this. And then we also have some kind of, in this case, precipitation. So so kind of meteorological covered information. Well, how to put this everything together? Our basic model is the framework of Gaussian Cox processes, right? So I'm just showing you the overall thing. The overall thing is that I have something which is a stochastic process, which is this capital gamma, which you see depends on space and time. And the integral in space, the integral in time of this capital gamma is the, let's say, the mean value to a Poisson distribution. And with this, what I have is the expected number, or our counting variable, which is the number not expected. This capital Y is the number of events, so the number of particular type of crime happening in region I and in a particular time interval Tj. So with this Poisson, this is fine. The only problem is that the model we put into gamma is kind of complicated thing, and so complicated that this is our capital gamma, our stochastic process. You see that this capital gamma depends very much on three terms: lambda in space, mu in time, and then the exponential of a space-time stochastic process. And we develop a little bit of mathematical things here inside. I'm not going into them, but the important thing here is that the two, let's say, deterministic terms are fine to deal with, and then the stochastic term clearly is a space-time stochastic process. As such, we need to develop a little bit of theory about what is the correlation, which is the covariance structure of this stochastic process, because that provides the, let's say, the stochastic, let's say, the stochasticity to our previous deterministic term. In any case, so the thing is that we are able to provide uncertainty on our expected values for, so in our forecasts, because we are able to obtain not only the expected value of what will come next in terms of time, but also the variance of this forecast. So our uncertainty measure. So with this model, the important thing here is that we can go to the police and say, fine, this is our probability map in these areas of the city and in these particular temporal, let's say, intervals. So, and this is what basically what the police asks for, in a sense. Fine. So just to, I'm not going here, but I just want to show you something like this. What we call the risk maps. I mean, when you go to the police, you cannot show them very complicated things. You just have to go there and say, this is your risk map. So, for example, tell me in which part of the city, in terms of space, there will be what is the map of the risk of having a car theft, or having a homicide, or a shoplifting, or burglaries, or whatever. But even more important than the risk map is what they call the exceedance probabilities, because they don't want to act if the probability is whatever 0.55. They usually have a threshold something like 0.85 onwards, and then it's no, tell me when I will be on top of 0.85, and then I will act, and then I will trust on this, and I will modify my movements of the patrols and whatever. So these are the exceedance probabilities in each one of the different types of crimes that we analyze there, and this is much more kind of helpful for them. And then the prediction, of course, as I said, like we can go in space and we can go in time in terms of forecasting and predict when the next car robbery will and when will happen. And then I think I'm running out. I just ran out, but so I'm not saying anything about this prediction, but I just wanted to go probably because this is something important for you. And I'm finishing with this reducing dimensionality. I mean, with nowadays technologies, clearly we are able to obtain lots and lots, and when I say lots, it could be hundreds of thousands or even millions of observations. And in terms of crime data, you cannot go to the police and say, no, this is my map for today, this is the map for tomorrow, and then showing hundreds of maps, because they don't have time, they don't understand, and in a sense this is boring for them. There is a way to do to reduce the information down to something which say, no, this map provides information of hundreds of them, and this is called body center. So what is a body center? And in just very informal way, a body center is a point pattern in a space that provides that point parent the same information, the same amount of information that a number of them. How to do that? We minimize something which is called a Frechet mean, and of course we need to define something which is, let's say, metrics, so distances between point parents, because one thing is distances between events, but if I have a collection of points and I have another collection of points, what is the distance between 2 point parents? So we need to define distances between, so new metrics, distance between point parents. And here in this approach, we define what is called, as you see on top of there, what is called the transport transform, the TT metric, and its corresponding normalized version, which is a way, it's a metric in the space of point parents. With this, we're able to obtain this sort of this thing in equation 7, that point parent, which is called the body center, that in a sense provides the minimum of this kind of weighted Frechet mean of all types of patterns. And with this, you can go to the police and say, for example, let me just go here, for example, now in Bogota, you can say, no, in 2012, you only have this point pattern. Of course, you have hundreds of them in the same year, but this is the body center of that year. So this represents basically the same amount of information of all individual point patterns and the same kind of thing. And with this, you see in 2017, you see that the body center, which is this point pattern on down right, which is clearly representing the whole variation of all point patterns of crimes happening in, this is for street theft, happening in 2017, and just clearly it clearly indicates an big increase of these let's say street thefts in the city of Bogota, or for example in the city of Valencia. You can say, no, I'm going to different we call barrios, like well, different, let's say, regions, sub-regions within the city, and define, for example, for winter time or for summertime, what is the corresponding barycenter. And with only that one map, with those events there, it represents the whole variability of all types of parents happening in winter and in those particular areas of the city. I think I will stop it here because then I could be talking for, let's say, 15 minutes more. This is very interesting. This is more mathematical, so I don't want to do this in just 1-2 minutes. But let me just so go to the very final thing, and then I will end up with this. This is, I mean, the very last thing I wanted to comment in only 1 minute is this thing of what happens when you have origin destination point parents. So just imagine that you have, like in this application, this was in a city of Mexico where we have, well, the city was divided by north and south of the city, but the important thing here is that we have a number of car thefts and a subset of them were recovered. And then the question of the police was something like, yeah, can I mean, knowing the location of where a particular a car was stolen, knowing that, can you tell me a little bit of where it will be recovered? So kind of joint and conditional distributions of the 2 point pairs: origin, which is where it was stolen, and destination, which is where it will be recovered. That was very helpful for the police, and we consider this is kind of, you see, where it was on the left hand side, thefts, so stolen, and where it were recovered, and again, without going into this, we develop an LGCP Gaussian Cox process as the one we developed for Bogota data, and we developed several things there just to provide information on this, let's say, conditional. For example, this is a conditional probability function, which was really useful for the police because they know where the car was stolen, but they didn't know where they would be, let's say, recovered. So let me just finish with these kind of sentences that highlight a little bit of what's important here, which is if you are working with crime data or you are working with COVID data, real-time surveillance is it's important. I mean, it's not a question that the police they need some cop forecast for the next 2 hours, and you say no, my model it needs to run one day, and then in one day time I will tell you something. The police will say no, I cannot wait. So real-time surveillance is really important. It means that when the data is larger and larger, we have new challenges in terms of computation, because that's very important. It comes together with a statistical analysis, computation. The big thing with this, and this is really motivating for me, which is solving real problems for society. I mean, whether you're working with crime data, you're working with infectious diseases data, I mean, this is a problem for society, and we try to help from our means that on what we can. No, so solving these real problems for society is something really important for us. And so I think that's all. Sometimes I went maybe too fast, but just wanted to give you this overall overview of different types of, let's say, statistical approaches to types of problems. Thank you very much.
Thank you, Jorge, for the very interesting talk. So many things involved there. I myself having many questions about everything, details, and so on. I look forward for you to send us papers about this. I'm sure it's a collection of papers, not only one. It's too many things involved.
Yes.
We have some questions in the chat. I will just project in the screen. If you would like to return to our screen, you'll probably
Yes.
see them. So Vinicius Marink is a faculty here. He's asking about the negative binomial model indicated from BYM, right? So he's asking if you face any identifiability issues between those quantities, the U and V.
Yeah, that is a good question. Yes, well, clearly we went to negative binomial as an alternative to Poisson distribution, right? Because of this over dispersion. This is kind of a classical strategy. But when we went to, let's say, within the negative binomial, we had these two parts. One part is let's say, the parametric term corresponding to covariance. We have no problem there. And the other part is these structure and unstructured terms. I know that sometimes there can be some kind of problems of identifiability between the two terms, but in our case, we didn't, let's say, encounter those sort of problems. If it comes the case where there are problems of identification between parameters of the unstructured and parameters of the structured term. Then you have to solve these issues, and some reparameterizations are fine. For example, the model has several alternatives. With reparameterization, the just thing. So I mean, there are ways out when you do those type of problems.
Okay. He has another question. You talked about specifying focus point earlier. Could you give more details about that?
Yeah. Yeah, focus. Well, I don't know if focus point you mean in the ellipse. The idea is that we transform our sigma, so the Gaussian variance covariance matrix, which is kind of stationary behavior, into ellipsoids. And the ellipsoids, they have two focus points. So basically, we visited each location, and in each location, we learned. This is why we use this neural network procedure. We learned the two focus points, and the two focus we learn two things. One, the direction, so the kind of orientation of the in between orientation of the two focus, and the length between the two focuses points. So this was a way to go from stationary to non-stationary procedures, and also to define this, well, not to define, because we had so many, because this has to be S by S, location by location. The computational problem is really large, so we just ended up using this kind of neural network learning procedure.
Okay.
I can
So,
show you. I can give you, if you have more, let's say, more information on this. Later, I can send you Marco, so that you can spread these papers.
oh yeah.
Yeah, sure. And this is clearly done on different papers.
Okay. So Paulo is saying hello. I know you know Paulo very well. He
Yes, I
also
know.
has
I know.
a question about this. Still on the focus points of the first part of the crime section. I guess they are outputs and not fixed in advance. Would it make sense to explicitly add them for the known case in the model?
Yes, I mean, when Pablo refers to, let's say, to the first part of crime section, yes, the idea is, for example, just consider these whatever police stations. So you have there several police stations all around the city, and you want to say if being closer to a police station increases or decreases, let's say, the crime risk, right? So clearly, this focus point or these, let's say, locations are, let's say, fixed in advance because they are located in particular places of the city. So this is not basically a point pattern itself, right? These are just focuses or what we call landmarks, locations where what is the crime activity close to them, how is the crime activity close to them. So we consider as in the model we evaluated distances each one of the, let's say, crime events to each one of these let's say fixed locations, and these are our DIJs that are included into our kind of transmission or maybe exponentially decreasing function, but they are not considered as a point parent. So it's not like the origin destination point parent, because the second one is, I mean, the second one, the locations of the fixed points are just fixed points. So they have no, let's say, stochasticity in them.
Okay. So Vinicio is saying thank you. Meanwhile, I got a question from Rosangela. She say thank you for the seminar, so on and so forth. She asks if you consider anything about the sub notifications of the COVID data. It's very common to have sub notification. If that's included in the model, or if you just use the raw data as it was.
Yeah, that's a classical and also a very good question. Yeah, well, clearly we have an underestimation. It's like human mobility. I mean, not all people. I mean, there were some. I didn't mention that because I went quickly through that. But the mobility data we have is an underestimation of the true mobility. It's kind of a proxy to the true mobility. The same kind of thing with this COVID data. I mean, although the data was clearly, I mean, handled by institutions that they were recording all type of data. I'm sure it is known that there is an underestimation of the true data. Well, this is the best we can do with you consider only as the raw data we had. We didn't control for underestimation. That is something that we could do in the future, but we didn't have any information on how this underestimation was done, so it was kind of difficult thing.
Yeah. So I think I have two questions for you. Well, I have several, but I will ask two. And a comment. I know Orange Destiny problem. It's a very interesting problem. And if you pass really fast the slides, even though I noticed you use our hometown as your example there, Belo Horizonte is where we live. I know Renato has worked with this as well, Assunção, and he has papers about this, maybe 2010
Yes.
or 11, something like that. And at that time, I was an undergrad student at the lab, and we working in, because that's a big problem in Brazil, right? A car gets stolen, where should you go? Where you find the car and this kind of thing. So it's a very interesting that you going back to this and improving the methodologies and so on. Another question I have, this velocity process you use is very interesting because it gives you a different interpretation from the common sense we have. And I noticed that is a JASA paper, 2023, from Sudipto, Aritra Howden, and Deepak Day about what they call the spatial curvature process, which is basically very close to what you presented. Have you ever seen that paper? Have a
Yeah.
comment to see what
Yeah.
are the
This
differences and
absolutely.
the same?
Yes, absolutely. In fact, this is an ongoing paper with Alan Gelfand, and Alan Gelfand, he knows very well Sudipto, and there is one or two papers that they mention a little bit about velocities, but the velocities they use is on the geostatistical term. In the geostatistical context, let's call like that, right? So what we do in our paper is bringing that or adapting that into the point process methodology. But yes, in terms of velocity, there exist not many papers, but at least two or three. You mentioned one, and there are two or three more, no more than that. But they are more on the geostatistical thing. Yes.
Yes.
Hmm.
And finally, I got a question from another professor from the criminology department. Are these tools available for criminologists or epidemiologists? Like he's asking basically, they are software, a package or a script that they can easily access because they are not programmers and so forth.
Yeah, yeah. I mean, we try to have our code available for each publication. So, what I mentioned for the crime data, also for the COVID data, we have our, let's say, GitHub web pages where we have the data associated to the publications, to the papers with these things. So, if any of you are interested in particular methods, just let me know, let Marcos know, and then I can provide the code.
Okay.
The
I
code
think
is basically in R. I mean, everything we do is
perfect.
R, sometimes in combination with Python, but most of that is R.
Sounds good. Okay, so let me thank you again, Georgia, for the very interesting talk. I guess we could keep talking and ask questions for a while, but the students have to go. They have other, things to do, as I know you have as well. So thank you for the great talk, and I'm very happy to have you here. Hopefully in person next time in Brazil to give us a talk, a seminar, a short course, something I know it will be really useful. So
Yeah,
thank you very much.
I would be happy for that. Yes, for sure. I know many people, friends, Brazilian friends. Yes.
That's great.
Thanks for inviting me again, Marcos, and thanks all. And just I'm open to any questions or any comments by email in this case.
Okay, so if you can stay just another minute, I will just end the transmission and I'll talk to you real quick.
Sure.
Bye bye, everyone.